Hello and welcome to Physics Tips for Cambridge Students YouTube channel. Today we are going to be continuing with our topic on work, energy and power. In the first video, we just laid the foundation of this work. What is work? The forms of energy, energy transfer and conservation. We also look at the concept of work itself and efficiency. In this one, we are going to be looking at kinetic energy and potential energy, as well as the concept of power. Please remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Like, share, comment, as well as hitting the notification bell so that you get alerted of my videos. Without much further ado, let's get started. Potential energy and kinetic energy. Potential energy is defined as the energy that a body possesses by virtue of its state. Gravitational potential energy is the potential energy that we normally use as a basis. Kinetic energy of an object is the energy that the object has because of its motion. Kinetic energy is equal to half mv squared, where m is the mass and v is the velocity of the object. Now, if you look at an object here, it has been subjected to a force F and it has moved a distance of s. We suppose that F is constant on the mass m and it is accelerated in time t from rest. Therefore, the resultant force is equal to mass times acceleration. Now we know that work done from a previous video is equal to force times the displacement s. We know that work is equal to the force, which is mass times acceleration times that displacement s. And we also know from the equations of motion that v squared is equal to u squared plus 2as, and we said that this object is starting from rest. So u is 0. So you can just say v squared is equal to 2as. The bit where we're saying MAS, so the AS part, we can just divide this by, so V squared divided by 2 would be equal to AS. So that's what we have here. So which means the work done is equal to mv squared over 2, which can be simplified further to just half mv squared. The work that's going to be done is equal to the kinetic energy that's going to be gained as the object is moving, starting from rest. In general, the work done on a body equals the change in the kinetic energy of the body, which we call the work energy equation. Half mv squared minus half mu squared is equal to the work that is done. Now let's look at this example. So the first one says that find the kinetic energy of a person of mass 60 kg moving at 70 meters per second in a plane, touching down in a runway. What force is needed to stop the person in a distance of 2,100 meters? Force times displacement is equal to half mv squared is the formula that we are applying here. The mass is 60 kgs and the speed is 70 squared. Then we multiply this by half. So this should equal the force that is needed in the distance 2,100 meters. So if you make the subject there, you are going to get 147,000 joules. And to get the force, you just divide by the distance, which is going to be equal 70 newtons. If the distance is 700 meters, you just substitute this for that, and then you get 210 newtons. So please do the question and find out whether you get the answer. It says, what supplies this braking force? So the question is talking about the plane which is touching down. So this is the force that is acting on the person to stop him accelerating further. This force is going to come from the seat belt that this person is putting on. The seat belt is designed to stretch a little and allows a greater distance in time over which the braking force acts, thus reducing the force on the passengers. Let's look at gravitational potential energy. Potential energy is energy stored available to do work. Now, gravitational potential energy is the energy an object has in a gravitational field because of its position or distance from a mass causing the gravitational field, which is given by delta EP is equal to mg delta H. Delta EP is the change in the gravitational potential energy, and delta H is the change in the height. Remember, we can only talk about the change in the gravitational potential energy, the change from where it started to falling on the ground or wherever it is falling to, or whenever it's gaining height to. Suppose you've got an object and that object is being lifted up. The work done to lift the object equals the potential energy gained by the object. Suppose the object is lifted at a constant speed, so the force equals the weight of the object. Work done is equal to F times H. Force F is equal to the weight, which is equal to mg, right? So the force that you're lifting up is the weight, so it's going to be mg. Mg and the distance is that delta H that we talked about. In this case, we are taking the potential on the ground to be zero. Let's look at this example to apply this concept. When the roller coaster is released from the top of the track at rest, it reaches a speed of 16 meters per second right at the bottom of the track. Use the principle of conservation of energy applied to gravitational potential energy and kinetic energy to show that the original height of the roller coaster was about 13 meters. In this case, you are told that u is zero, so that is it starts from rest. So what it means is the gravitational potential energy that it had here is equal to the kinetic energy that it will have at the bottom. The mg delta h is going to be equated to half mv squared. So the m's cancel out, and then you remain with the g delta h is equal to half v squared. Now making delta h the subject, you are going to have it as v squared over 2g. And if you do that, you get 13 meters. Now in part B, it says that in another run, the car started from the same height but was given an initial speed of 10 meters per second. Show that the speed of the car at the bottom of the track was about 19 meters per second, and asked to take g as 9.8. When it started initially at this point here, we are told that it had an mg delta h plus and half mu squared. That is going to be equated to half mv squared. So that will be our equation for the movement of this roller coaster. Again, the m's cancel out, and then you have g delta h plus half u squared is equal to half v squared. We already know that our h is 13 meters, so you're just saying that g delta h is 9.8 times 13 plus half times 10 squared, because you told the u is 10 here. So 10 squared should equal half v squared. So if you do the maths there, please verify this. You should get, in fact, they said sure that it's going to be 19 meters. It's going to be 18.86, which is rounded up to 19 meters per second. Right, moving on to the next example. Says that a car of mass 1000 kgs increases its speed from 10 meters per second to 20 meters per second whilst moving 500 meters up a road inclined at an angle alpha. Let's just change this to theta to be consistent with the diagrams. The angle theta to the horizontal, where sine theta is equal to 1 over 20. There's a constant resistance to motion of 300 newtons. Find the driving force exerted by the engine, assuming that it is constant. Right, so in order for this car to move upwards, the work that the engine is going to provide should equal the potential energy gained, the kinetic energy gained, and the work done against resistive force. So the work done by the engine is the PE gained plus the EK gained plus the work done to overcome resistive forces. In order for us to get the PE gained, remember it's going to be mg delta h. And this one is going to be half mv squared minus half mu squared, the kinetic energy gained. And then this is just going to be force times distance. So where we're saying the force due to the resistive force times the distance. So first, yes, times the distance. So this is equal to the force by the engine times the distance moved. Now the distance moved is 500 meters. We are given sine theta is equal to 1 over 20. This is also equal to the distance that's going to be gained in the vertical. That's our h over 500, because that's the same thing. Sine theta is equal to h over 500. The distance moved along the plane is 500. So to get h, you just say 500 times 20. Sorry, this will be 500 over 20, which gives you 25 meters. So to get the potential energy gained, it's going to be the mass, 1000 kgs, times g. We are given, we are told to use 10. So 1000 times 10 times 25, which is going to be 2.5 times 10 to the power of 5 joules. And then for the kinetic energy, that's half m times 20 squared minus half times m times 10 squared. So that should give you 1.5 times 10 to the power of 5 joules again. The resistive force we are given is 300, but it's acting on a distance of 500. So it's going to be 300 times 500, which is going to be 1.5 times 10 to the power of 5 again, joules. To get the work done by the engine, which is the driving force, 2 times the distance moved, is going to be the total of all this here. That's going to be 5.5 times 10 to the power of 5 joules. But the question wants us to get the driving force itself. So you divide by the distance d, which is 500 meters. So F will be equal to that 5.5 times 10 to the power of 5 divided by the distance 500 meters. It should give 1.1 times 10 to the power of 3 newtons. The next example here says sketch graphs to show the gravitational potential energy and the kinetic energy and the total energy of an object falling from rest, how these vary with time and with distance falling. Now, if you're to look at the total energy, is always constant. Remember, from the law of conservation of energy, we say that there's no change in its total amount. So total energy would just be a graph like this. So that is total energy over time or over distance is still the same. But then when you look at the relationship between gravitational potential energy and kinetic energy, so that will be EP for gravitational potential energy is equal to mg delta H. Now, if you've been asked to find the relationship between EP and the time, you try and change this right hand side so that you have time at least incorporated there. So the equation that comes to mind when I'm talking about this is S is equal to UT plus half AT squared, of which A is G in this case. So S is the distance or the height. So if this is falling from rest, then we are saying that mg, then this will be half gt squared. So what it means, this is a constant, mg is a constant, then there's another g, so it becomes g squared. So half mg squared t squared is the one that's related to EP. So as you can see, this is a quadratic function if you're to plot against t. So which means a quadratic function, but also bearing in mind that this thing is falling, which means that the gravitational potential energy has to decrease, not increase. So it starts at a certain value and then it decreases. So it's an inverted, it's a quadratic graph, but that is inverted like that. The corresponding kinetic energy graph would be the opposite of this. So it rises up. So EK rises as EP falls. That's how it's going to be. So if you have the two graphs on the same axis, you find that one will be falling the other one will be rising. Like that. And there's a moment when the two are equal. So this is with time. And then with a distance fallen, for the kinetic energy, we use the formula V squared is equal to U squared plus 2AS. I think that is 2GS. So again, starting from rest, so that is that. So V squared will be equal to 2GS. And the kinetic energy is half mv squared, so we just take the 2gs as it is. Now 2g is a constant, so it means it's v squared versus s, so kinetic energy versus s. So it's just going to be a straight line like this. So ek versus s is a straight line passing through the origin. So which means the corresponding ek or ep graph is going to be falling down. So this is for ep, and then that one is for ek. I hope it makes sense. Now, lastly, I'm going to talk about elastic potential energy, that is Hooke's law. This is the energy stored in a spring obeying Hooke's law when it is stretched. This can also happen when it is compressed and deformed. The spring is undergoing an elastic change because there is no permanent deformation. It retains its original shape and size when the load is removed. Elastic potential energy is given by half Fe. So this comes from the graph here of F versus E from your IGCSE Hooke's law. F is directly proportional to E, the extension. So the area under the graph would be equal to the work that is done. So half Fe. Now we know that F is equal to Ke, so which means it's going to be half Ke squared. There is a problem to work out. So the suspension spring of a car requires a force of 100 newtons to depress it 1 centimeter. So this becomes the compression. So compression or extension have the same meaning when we come to applying the formula. This is how much work needs to be done to compress it by 5 centimeters. So first of all, we get the constant. So we said F is equal to Ke. K will be equal to F over E, which is 100 over 1 times 10 to the power of minus 2. Once we get that, we can now apply it. Says how much work is done. Now work is equal to half Ke squared. So which is going to be equal to half times that K, 100 over 1 times 10 to the power of minus 2 times E squared, which is 5 times 10 to the power of minus 2 squared in joules. If you do it well, you're going to get 12.5 joules. Next, there's an example here. It says in a pinball machine, a force of 24 newtons is used to compress a spring a distance of 0.080 meters. Find the potential energy stored in the spring and hence find the maximum speed which it can produce in a ball of mass 0.15 kgs. The potential energy stored is equal to half Fe. So the extension is 0.08 is given there. So it's going to be half times 24 times 0.080. If you do the maths there, you should get 0.96 joules for this one. Then the question further goes on to say the maximum speed which it can produce in a ball of mass 0.15 kgs. So we're saying that this EP should equal the EP lost as it is now stretching back. Because remember, this has been compressed. As stretching outwards, it's going to cause a change or an increase in the kinetic energy. So we're going to equate the EP to the EK. 0.96 joules should equal half mv squared. And then we make V the subject of the formula. So V will be equal to the square root of 0.96 times 2 over the mass. The mass is given in the question, which is 0.15. So if you do the maths well, you should get 3.6 meters per second. Now, to end the video, we are going to talk about the concept of power. Power is the rate at which work is done or the rate at which energy is transferred. So in formula terms, we write P is equal to W over T, or delta E over delta T, or that is the energy transferred over the time taken. Now the unit of power is the watt, and 1 watt is equal to 1 joule per second. Power and velocity. For a car or boat moving at a steady velocity v, the driving force of the engine is equal to the frictional force, so there's no resultant force acting. So power is equal to delta W over delta T, which is equal to, since delta W is equal to force times displacement, so it's going to be force times displacement over the time taken. Let me write it here. So power is equal to W over T, which is equal to force times the displacement. Let's just give the displacement S over T. We know that S over T is equal to velocity. It's going to give us F times the velocity V. Then I'm going to end the video with this example. The motorboat is moving at a steady speed of 15 meters per second and resistance to motion is 15,000. Calculate the power output of the engine. So power output is just equal to force times velocity. The force is 15,000 newtons and the velocity is 15 meters per second. So if you do the maths there, you should get 225,000 watts. I'm going to end the video here. Please remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Like, share, and comment, as well as to hit the notification bell. Signing out.